Hey, hello everyone. I hope all of you are doing good and enjoying mm, being out of the comfort zone, right? Learning. If you think learning is fun, then definitely you are enjoying, right? Great. So let's continue, right? Yesterday we had done we were doing the fundamentals, the basics of logistic, right? No, we started with logistic and we were now and we had done the conceptual part of the logistic, right? All of you can see my screen. Just a sec. All of you can see my screen, right? I had discussed what is logistic, right? I will share this entire PDF, so don't worry about it, right? So, right. So now this is the sigmoid transformation, and as I said, this is not required, but yeah, if you are interested, you can go through it. Okay, so the concept part of logistic is clear, right? It is basically the important thing is we are here predicting the categorical variable based on the probabilities, right, of whether that event will happen or not, right? So logistic, when we run logistic regression, you'll see we'll get the probabilities. Okay, so let's continue from here. I want all of you to go to R, and I think I'll have to share. Wait, I'll share the logistic. Just wait. So, am I audible? Am I audible? Okay. James, James, am I audible? Um, can someone help James? So I've shared the files for logistic. Please take out the files and you will see a data set called LR diabetes, right? LR diabetes is the data set we will work on. Okay. So we are going to start by importing this file LR diabetes, and let me just open this file and discuss with you the data. So this is a file, and if you can see, there are some variables from A. A is just an index number, right? Just a count, right? From B, C, D, E, F, G, H. These are the input variables, and I variable is the uh, dependent variable, right? And it's in the form of 1 and 0, right? It is basically based on the input variables. We are trying to predict whether a person will get diabetes or not. This is the case, you can say, right? So to predict if a patient is diabetic or not based on the given data. Is that clear? So quickly I want you to import. No need to set directory and all these. Simply import using file.choose and pick up the data. Once you're done till line number 12, let me know. Line number 12. Once you're done till line number 12, let me know. And please, can we speed up? So view will help you view this data. Then structure and summary I'm running. I'm running these two commands just to understand the data. Line number 12 is done. Please type 12 in the chat window if it is done. Okay. Let's understand the metadata or the data dictionary, right? Npreg is a variable, right? Integer. It is number of pregnancies. GLU, plasma glucose concentration. BP, diastolic blood pressure. Skin, triceps skin, tricep skin fold thickness. BMI, body mass index. PED, diabetes pedigree function. You need not, as a data scientist or as a, you can say, I mean, data analyst, you might not be aware of all these technical terms. And that is why industry expertise is needed, right? That is why we need help from industry experts. Okay? Age in years. We have age in years. Then type. 1 is yes for diabetes. 0 means no for diabetes. Is it clear? The data is clear? Now, let's look at this structure output. What do you think? Which data type we should be changing? Which data type is not correct? It's an easy question, not a difficult question. But yes, I just want you to apply a little bit. Just think, what exactly do you think we should change the data type of one, at least one variable? No one? Uh, Type. Yes, yes, right, right. Yes. Type. Yes, right. What should be the data type? Type is right now integer. Correct. Not Boolean. We'll change it to factor variable. Right? Because see, we all know logistic. When we are doing logistic, the dependent variable is not numeric, and right now it is taken as integer. Right? So all integers are numeric anyways. So I'm going to change this type. Okay, great, James. James, you want to quickly? I've shared the files. Take this link and just pick up logistic regression in the end. Download this folder. In that, there is a data set LR underscore diabetes. Just import that. Okay, so I will change type to a factor variable using as dot factor. Once you do it, I'll check the structure again and I can see type variable has been added. So there is one initial, type also exists and a new type variable has been added with two levels. Notice and notice now here two levels 0 and 1, right? And in the output it is giving 2 1 means 2 means 1, 1 is 0. Is that clear? 2 means second level, 1 means first level. Is this clear? Now I'm going to split this data into or test and train and do cross validation. So use, I hope you have already downloaded CA tools when we are doing cross validation. So all you have to do is run library CA tools. If you have not downloaded CA tools, if you have not installed it, just install .packages CA tools. After that, library CA tools. And then I use set.seed to fix the randomness. Set.seed and then I run sample.split on type and split ratio I keep it as 80-20. So please do it till 44. I am waiting. Once you're done till 44, let me know. Okay, I'll wait for more confirmations. Okay, so 44, once you're done till 44, let's check the split variable. You'll see true and false, right? Because true means all the records that are part of train data, and false means all the records that will be part of testing data, right? So then I use subset and create two variables, train.diab, which will have training data, and test.diab, it will have test data. Train.diab and then test. Once you're done till 60, let me know. After you do 60, write 61 as well. Attach train.diab because we are going to now create a model on training data. Do till 61. Okay. Once you're done till 61, now LM was used in linear model. In logistic regression, we use GLM, generalized linear model. Okay. So GLM, and if you notice in both these cases, I have forgotten, or rather I did not remove this type, right, which was integer. So I am just removing it here. I'm saying GLM type 1 tilde dot minus type means exclude type. Include all the variables but exclude type. Data is equal to train dot diab and family is equal to binomial. We mentioned this family is equal to binomial because your output variable is logistic, right? Oh, sorry, is a categorical variable. So just mention family equal to binomial. Very similar to that in uh, linear regression, you get a output like this, summary. If I run summary, I get a output like this. It's very similar to, you can see, quite similar to linear. So do till summary, line number 78. 78 is done. Others, can you see the output? It looks similar, but it is actually different, right? Notice we have some different terms here. There we had adjusted R square, right? Herein we have null deviance, residual deviance, AIC, Fisher scoring iteration, and then this part is same. Even this is same. Okay? And here we have Z value, there we had T value, right? Okay, so let's understand this output, right? Starting with what is, star ratings we already know. Triple star means you are 99.9% confident that the variable is significant. Double star means you are 99% confident. Single star means you are 95% confident, and dot means you are 90% confident that the variable is significant. Okay, so you see a term here called null deviance, right? So null deviance, if I first let's understand what is deviance, right? Deviance, you will find null deviance and residual deviance. That's why first let's understand what is deviance. Deviance is a measure of goodness of fit of a generalized linear model. Means how good the model is fitting the data. Deviance tell you that, right? Basically it tells you the um, it gives you an idea on the variance, right? So null deviance. Now coming to null deviance. Remember we in regression, linear regression, where did we start our linear regression from? If you can recall, we started from base model, right? Which was y average, right? It was average of y, mean of y, right? So here also the approach is similar. Null deviance indicates the deviation of the response from the actual predicted by the model when no independent variable, right? When no independent variable is included or predicted by the model with no independent variable, but only the intercept. Okay? Lower the value, better the model. Is that clear? Clear what is null deviance? Okay. Pungodi. Null deviance is simply the deviation of the response from the predicted, right? Of the response from the actual predicted by the model with no independent variables. Okay. So basically it is saying when you do not put any independent variable there also, first thing we did was we came up with a base model with no independent variables, no x variables, right? Same here, right? When you do not have any x variables, what is the deviation of the response variable, right? Deviation of the response from the actual. Is that clear? So of course, lower the deviation, better it is always, right? So lower the value, better the model. Is this clear? Okay. Then you have residual deviance. Null deviance indicates the deviation of the response. This should be residual, right? Residual deviance indicates the deviation of the response from actual predicted by the model on adding independent variables. So lower the value, better the model. Of course, lower the residual deviance, better the model. Now, when you consider these two together, right? More the difference between null and residual, better the model performance. I mean, just think there also moving from base R, right? Here also it's like we are moving from null deviance, and so more the difference between null and residual, better is going to be model because model has improved the deviation. So which among null and residual do you think will be a bigger number? Let me see if you can. Which among this will be a bigger number or a bigger variance or deviation? Residual. Residual? Why? See, one is without putting any independent variables. Then when you put more independent variables, what will happen? Your deviation is going to reduce, isn't it? Logically think, right? One first is null, which is without any independent, I mean, no input information. But as you put more information, you are only going to reduce the variance, isn't it? Is that clear? Okay. So now you'll also see some degrees of freedom here. For null deviance, the degrees of freedom is simply n minus 1 because we do not take into account any independent variables. So number of observations minus 1, right? So if you see here, how many observations were there in test data, training data? Okay, you will have to tell me. How many observations are there in training data? Let me see, you can tell quickly. 265, right? So notice the degrees of freedom of null. 265 minus 1, right? Okay. And then degrees of freedom of residual deviance is n minus k minus 1, where n is the number of observations and k is the number of variables used in the model, right? So can you tell me how did we arrive at 256? Just write the calculation. 265 minus 8 minus 1. Okay. Is that clear? No response. Okay. Is that clear to all of you? And notice null deviance and residual deviance. Which is bigger? Null, of course. Okay. Can I proceed? So, degrees of freedom associated with null and residual differs only with respect to k. You can see this, right? Okay. Then there is this metric called AIC, Archaic Information Criterion. AIC is Archaic Information Criterion. Okay, notice it here. AIC 238.64. Yes. AIC in logistic is analogous to adjusted R square. Let me see who can recall adjusted R square. What is adjusted R square? Degree of fit. Uh, Goodness of, yeah, degree. But what was the main most important point? What is how does the adjusted R square? It's basically, if you can recall in regression, it's basically it measures the strength of the model, right? Modified version of R, then what is R? It basically measures the strength of the model. Okay, how good the model is capturing, how much my model is explaining the variation or the errors, right? Explaining the errors. Is that clear? Okay. So now AIC in logistic regression is analogous to adjusted R square because it also tries to prevent you from including irrelevant variables, predictor variables. So it is a measure of goodness of fit, means how good my model is fitting the data, which penalizes the model for more number of coefficients. Okay, which and it penalizes the model for the number of model coefficients, basically more number of model coefficients, means more number of independent variables you are using, AIC will be less, right? Sorry, AIC will become more. Okay, useful, it is useful when we have to compare the goodness of fit of more models, right? It is useful when we have to compare the goodness of fit with respect to more than one models. It is the maximum likelihood estimate, means how well the model predicts the data, right? Maximum likelihood estimate means how well the model is predicting the data, which penalizes to prevent overfitting, right? So it penalizes the model for overfitting and prevent overfitting. It measures the flexibility of the model. Lower the AIC, better the model. Okay, this is important. Lower the AIC, better the model. Okay, so but of course there should be, if you are comparing two models and the lower AIC means in terms of goodness of fit, in terms of it's better in the sense that the one with the lower AIC is predicting, is using less variables comparatively to predict to get the same results. Okay, the best fit model according to AIC is the one that explains the greatest amount of variation using the fewest possible independent variables. Is this clear line? Is this line clear? The best fit model according to AIC is the one that explains the greatest amount of variation using the fewest possible independent variables. Clear? What is AIC? So now that we know these terms, okay, this is one last term, Fisher scoring iteration, though it is not used to evaluate any model, but it is basically the number of iterations that have been done when the model was created at the back end, right? So not basically not much used in uh, coming up with the final model. It is not used in deciding which model we should. But yeah, you should know Fisher scoring iteration, like in our case, it is 5. Means there were 5 iterations that were done, and then this model was given out. Okay. So Fisher scoring algorithm is a deviation of Newton's method for solving maximum likelihood problem numerically. It tells you how the model was estimated. The algorithm looks around to see if the fit would be improved by using different estimates. If it improves, then the model moves in that direction and then fits the model again. So basically iterations. In short, there are some iterations done at the back end, and the model just try to deviate a little bit the values and see if the results are improving or not. Right? So 5 iterations it has done. The algorithm stops when no significant additional improvement can be done. So, and it freezes the model. Okay, not much use in, as I said, it is not much used in evaluating the model, right? Okay, so now we have seen, we know all these, right? So let's take a look at the output. I have a null deviance, I have a residual deviance, AIC, and Fisher scoring iteration. Now what I will do is, this is all the same thing, I've just written it here also. Okay, AIC we have done, yeah. We have to optimize the model. To optimize the model, we'll remove the independent, yeah. So now what we'll do is, you can see there are some variables which are not significant. BP, skin, age, right? So what I'll do is, I will, to optimize the model, we will remove the independent variables for these independent variables from the model one by one to arrive at the final model. Basically now we are trying to do some iterations, right? Uh, as I said, coming up with a final model is a iterative process, right? It will require you to just uh, use different iterations, uh, use different combinations of input variables and see how the output is behaving, right? How the output variable is coming. So to arrive at the final model, residual variance should not be increased and AIC should decrease. So what is it saying? Make sure when you are deciding the model, the residual deviance, right, should not increase much and AIC should decrease, right? Should not, residual variance should not increase much, because this, we are already moving from 335 to 220, right? I've already achieved this. So if I get a model which has a residual deviance of, let's say, 250, I will not go with that. Okay, I will rather go with this. Okay, let's remove age. Let, iteration 1 we are doing, removing age from the model. Quickly do this. Remove the age. You can just copy that previous one and put a bracket around type and include age in it. Rest everything is same. So I name it as model 1 and I run. So if you can see, my AIC reduced 238 to 236, right? And my deviation, residual deviance 222.79 and 222.64, slightly increased. Residual deviance slightly increased. Yes. So residual variance slightly increased. Deviance rather. I've written variance. But AIC decreased, right? So as per AIC, which is the better model, which has lower AIC, right? Is this clear? Now when this means that age is a significant variable and cannot be excluded from the model because residual deviance, see, residual deviance moved from a little bit, it increased a little bit, but AIC decreased. Hmm. So, and what are the rules? Lower the AIC, better it is. Yes, lower the AIC, better the model, right? But what is happening is here AIC lower, it is better. Also deviance is low, better it is, right? So from deviance perspective, I would say it's better, but from AIC perspective, it is not better, right? Wait, AIC has reduced. Sorry, AIC has reduced. So lower AIC, it is better, right? And from deviance perspective, it has very slightly increased, right? From 220.64 to 220.79. So because deviance has increased, I can say that age is slightly significant. I mean, if not very significant, but it is significant because it has led to a increase in deviance, right? So what we'll do is we will again try another iteration. This time what I'm doing, I'm just removing BP. Okay, I'm just removing BP. Let's call it as model 2. Run summary and see what happens this time. Residual deviance increased 220.221 and AIC also increased. Residual deviance increased and AIC to become 237. Earlier it was 238. 238. From 238, AIC has reduced to 237 and residual deviance moved from 221 to 222. Sorry, 220 to 221. So deviance has increased, right? So what does it indicate? That okay, even if I remove BP, it is again impacting my deviance, right? In a negative way, means it is leading to a high residual deviance. So I may choose that I will not remove BP also for now, right? So let's go to the third iteration wherein I am removing NPreg. Please do it. When you remove NPreg, and I compare, when I remove npreg, my AIC become 247. Earlier it was 238. So it means, and let's take a look at 231. Deviance has become 231. Earlier it was 220. So of course, if I look from deviance perspective, I will not remove npreg because it is leading to a increase in deviance, right? Residual deviance. Okay. Last variable we'll try with is skin. So let's name it as model 4 and run it. Let's see what story does skin tell us. It says AIC is 236. Earlier it was 238. So with all variables, AIC has AIC was 238, but now it is 236. Okay. No, I have, this is summary for 4. Just to compare it, I have also asked for summary only of the base model. Okay. This is the 4th one. Okay. So that I can compare it, otherwise it would be very difficult, right? So 238, residual deviance was 220 earlier, now it has become, okay, 220.9, not much of a difference. Okay. And AIC is 238, earlier it was 236. So what do we conclude? That this variable skin, we might, uh, it is increasing the deviance, right, and decreasing AIC, right? So you can see they both are actually working. I mean, they both are moving in reverse direction, right? So now it's up to you to select, I mean, which variable I will be removing. Again, I am going to take help from industry experts that if this is a variable that is not required to be removed. Okay. So predicting values and checking. Oh yeah. So what we'll do is we are, when we uh, consult industry experts, right? They tell us that you can remove skin from the final model. Okay, because skin and diabetes, they are not related. Okay, so we will remove skin and let's use model 4, right? The one in which we have removed the skin. We will use that model for prediction. And let's see if we really, if our prediction is better than when we have included all the variables. Okay. So from line number 170 to 175, we are we are creating the predictions. So notice that predictions of a logistic model is giving you some probabilities, right? Okay. Once you do till 175, let me know, then I'll explain. Do till 175. So in, in line number 170 and 71, I am testing model 4, and in line number 174 and 175, I am testing model on test.diab, testing data, right? So let's take a look. RES, this is variable, right? RES, the model, the one that we created the first time, right? RES gives the probabilities of the patient to have diabetes. Now, this is giving you what is the probability of the third patient to have diabetes. Okay, is that clear? So these are the probabilities that the patient will have diabetes. So patient number 3 uh, has a probability of 0.04. In our case, it's 0.3. This is just ignore it, right? Uh, this was maybe I've written it wrongly or some other percentage, right? Some other probability. Check this in the test data. So if this has a probability of 0.03, right? Probability, and this is the probability that patient will have diabetes. Okay. So if only 3% is are the chances that the patient will have diabetes, should we classify third one as having diabetes or not having diabetes at a 50% cutoff? At 50% cutoff or 50% threshold, where will you classify this as? Having diabetes or not having diabetes? Not having. Others, did you get it? Not having, because it is less than 50%, right? So now what we do is we will predict this. We have seen based on these probabilities, we are going to predict and then check the accuracy of the prediction. Okay. So this test.diab, right? You can see the third patient had is 0, not having diabetes. And what is my model predicting? Not having diabetes. So correctly predicted? Yes, you all said not having, and my my test data also said it was not having. Are you getting this? Yes. So first prediction made correctly. Second, 0.05 62482, right? Again, this is, let's say, not having diabetes. And what does our, it is not here, it is say, it says it is having diabetes, but my data indicates not having diabetes. So there is a contradiction. Clear? Let's look at one more and then we'll third one. 14, 0.607 So 0.607. Uh, 60. So you will say it as having uh, probably having diabetes, right? The 14th person. And what does our data says? It is again a contradiction, right? So this is how you compare the actual and the predictions, right? And then we create a table from these, right? And this is called, when you create this table using table command, I create a table using the table command in which I mention actual value is equal to test.diab for type 1, right? This is type, or you can see type also, right? Type or type 1. This is my actual value, and predicted value is equal to RES4 greater than 0.5. I'm saying, putting the condition RES4, this is RES4. Fourth, right? I think I missed fourth. Yeah, here it is. All the RES4 values greater than 0.5. Okay, that is the prediction coming from the model. And actual situation is, are you getting this? How do you check? Right? Now, once you have created this table, right? Let's run this table and CF4. Once you do this, let me know. Or if you want any previous code, if you have missed it, let me know. Once you're done till 194, let me know. Till 194 if you're done. I'm just coming back in a minute. 194. Are you getting this confusion matrix? This is called confusion matrix. We'll see what is it. First, create this. Now, for categorical variables, for models wherein you do classification, right? This is a very important tool of measuring the accuracy, confusion matrix, right? Notice how it is created. It is saying predicted value false and actual also false. 39 of them, right? Predicted false and actual was true, only 9. Predicted true and actual was false, 6. And similarly, right? So all the values in the diagonal, right? All the values in the diagonal are the correct ones, right? So you can find the accuracy like this. 40, let me put it as 39 plus 13, 39 plus 13, 9 plus 6. So this is the accuracy rate. Got it? This is the accuracy rate of CF4. And let me check the accuracy rate of CF1. 38 plus 13. Thirty-eight plus 13. So we were able to improve upon accuracy. Can you see? From 76 to 77 with less number of variables. By removing skin, I was able to improve upon accuracy, right? Is that clear? Yes. Once you're done till 200, let me know. Now we have seen a bit about confusion matrix. Okay, couple of more confirmations on 200 quickly. Okay, so we have seen confusion matrix, right? Now let's see what is a confusion matrix, right? And if you will try to just uh, compare it, it looks like our error matrix. Remember that errors, hypothesis errors, right? It looks very similar to that. If you just, read it closely, right? It is a tabular representation of actual versus predicted, right? Okay, first confusion matrix is a performance measurement tool of learning classifiers, machine learning classifiers. Classifiers means classification algorithms. Okay, it is a tabular representation of actual versus predicted. This helps us in finding the accuracy of the model and avoiding overfitting. Okay, so it helps us in avoiding overfitting and finding the accuracy of the model. It is a performance measurement tool for learning ML classifiers. It is used to measure recall, precision, sensitivity, specificity, and more importantly, AUC ROC curve. We'll see all of these now. Okay. So understanding the confusion matrix, these are the predictions and these are the actual, right? So predicted was 1 positive, but actual was negative, right? So what would it become? False positives, isn't it? You are wrongly predicting 1, false positives. Is this okay? Next, predicted was negative, actual also negative. So true negatives. Okay, TN. Predicted was positive, actual also was positive, so true positive. Predicted was negative and actual was positive. So true, sorry, false negatives. Is that clear? So what are false positive? Rejecting a true null hypothesis. Something, right? False positives. Rejecting a true null hypothesis and going with a wrong one. Same here. Going with a wrong one and rejecting a true null. Right? So this is a type 1 error only if you see closely. And here this is a type 2 error only. False negatives. Wrongly mentioning wrongly predicting a negative when actually it was a positive. Okay, clear? Till here it is making sense. Now, true positive, I've just explained all of these, right? Which are same. Now, what is the accuracy of the model? We have already done this. True positive plus true negative upon all of them in the denominator. All the 4 quadrants in the denominator and true positives and true negatives in the numerator. That will give you the accuracy of the model. Okay. Now, there are some terms called specificity, which is the true negative rate. Means of all the negatives, how many negatives were correctly predicted? That's called specificity. Of all the negatives, I'm repeating, of all the negatives, how many the model predicted correctly? That is called true negatives. True negative is clear. Specificity is clear. Specificity is clear to all of you. Okay. Then sensitivity. Just like it measures the true negative rate. Sensitivity measures the true positive rate. Okay. Sensitivity measures true positive rate. So it will be of all the positives, how many the model predicted correctly. Okay. So true positive upon true positive plus false negatives. Okay. Then you have 2 more matrix. False positive rate. False positive rate, either you can straight away do 1 minus specificity or false positive upon true negative plus false positive. And lastly, you have false negative rates. Of all the negatives, oh sorry, 1 minus sensitivity. False negative rate. So false negatives upon true positive plus false negatives. So is this clear? All the four? Let me know if you want to take a minute to absorb, quickly absorb it, and then we'll proceed to the next slide. Quickly, 1 minute, just take a minute and just review it quickly. Is it done? Can we proceed? Yes? Okay. Others? Okay. Now, we have calculated these, right? Now, and we can see the accuracy. We can very well see the accuracy of the model with this confusion matrix, right? Specificity, if you want to calculate specificity, how many zeros was zeros I was able to predict correctly, right? True negatives. So this will be true negatives and positives also. Sensitivity. Okay. Now, once you have checked the accuracy of the model, right, from confusion matrix, I can very well see that model 4 has improved my accuracy from 76 to 77.6, right? Now, an important thing here is to note that we should try to minimize the number 7. Sorry, yeah, not number 7. Rather, we should try to minimize the uh, this uh, false. Wait, we should try to minimize the false positives. This number, okay? Because what is happening here? Here, I'm saying predicted value was false, but actual value was true. Means I have actually someone was having um diabetes, and my model has predicted he is not having diabetes. So we should minimize this. Sorry, right? What is the other error? The person is not having diabetes, but I am saying he is having diabetes, right? Right? So which one of these do you think is more dangerous for life? I am repeating. Just understand this well. Yeah, 9 is more dangerous. Good, you got it. Let me repeat it for the benefit of everyone. I think uh, first, and model prediction is not having diabetes, and actually person had diabetes. And second option, prediction was having diabetes, but actual was not person did not have diabetes. Right? Now tell me, looking at these two, which situation is more dangerous for life? Is it situation 1 or situation 2? 1. Why? Anyone? Why? Because we are ignoring the person who is having diabetes and he will not be treated. right? Rather than a person who did not have diabetes and we made it, we maybe we put him under treatment, right? So it's always now the first one is type 2 error, if you can recall. It's a type 2 error, right? And the second one is type 1 error. In hypothesis, what is type 1 error? Rejecting a true null. What is type 2 error? Fail to reject. Not rejecting or fail to reject. Correct, right? Fail to reject a true null, right? Okay. So failing to reject a, fail to reject a true null, right? Okay. So type 2 errors are always more dangerous. Remember this. Okay. With this discussion. And I think I had a discussion about this earlier also, right? Okay. Now there is another tool called ROC curve which helps you uh, measure or which helps you uh, understand the accuracy of the classification models. Okay, so for creating this ROC curve, I want you to quickly install and activate this ROCR package. I'm sharing it. Quickly activate and install. In the meantime, I will explain what is ROC. Right. So ROC is called receiver operating characteristic curve. Okay, receiver operating characteristic curve, and AUC is the area under this curve. Okay, now see, ROC curve is created using, is formed, it is a probability curve. Okay, it tells, yeah, ROC curve is created using two metrics: true positive rates and false positive rate. Okay, true positive and false positive. Okay, so tell me, for a better model, what will be your how will you optimize the model? By maximizing true positive rates, isn't it? True positive means positive as positive, so won't, right? So by maximizing true positive rates, I can optimize my model. And in terms of FPR, false positive rates, it can be optimized by minimizing this error. These are errors, right? False positive rates. This is an error. So my model will be better if I'm able to maximize TPR and minimize FPR, isn't it? Are you getting this, everyone? Right? Somewhere, somewhere at the curve bend. Yeah. I'm coming to that, Alok. So tell me, hypothetically, if I can do that, maximizing my TPR, right, and minimizing my FPR, won't my ROC curve be something like this? Hypothetically, though, I mean, it will maximize my TPR and minimizing my FPR means almost doing zero FPR. So it is, are you getting it? So if I'm able to predict, if I'm able to minimize my model and maximize, basically optimize, this should be my ROC. But that is a hypothetical case only, right? The other way is minimizing, uh, sorry, maximizing FPR and minimizing TPR. So if this is my if this and this are actual, what will be the area under the curve? It will be 1 only, right? If this, I mean, this is 1 because this is 1. Here TPR is 1, right? Because we have been able to correctly identify all the positives as positive. So probability becomes 1, right? And here FPR becomes 0, right? So what will be the area under the curve under this hypothetical case? 1. And this divides it into half, 0.5, right? So, but in real scenarios, your ROC curve would look something like this, isn't it? Now this is a hypothetical case, right? So higher the area under the curve, now higher the area, you can see the deeper this, the deep this you can say curve is, right? The better it is, right? So it means higher the area under the curve, better the model in predicting false as false and true as true. Are you getting this? Are you getting this? Yes? Okay. Thanks for the response. The ROC curve is plotted with TPR, true positive rate, or sensitivity. That's the sensitivity. And against the FPR, which is 1 minus specificity. So FPR is 1 minus specificity, right? Where TPR is on y-axis and FPR is on x-axis. Now, all this I have explained. AUC near 1 means which has good measure of separability, where AUC 0 means worst measure of separability. In fact, it is predicting 0 as 1 and on 1 as 0. And when AUC is 0.5, it means model has no class separation capacity whatsoever. Okay. So you got the concept of ROC and AUC. It should be AUC. It's written AOC. It should be AUC. Is that clear, everyone? Any questions on ROC? Let me know. Okay, then. ROC is a common way to visualize performance of a binary classifier. A binary classifier has two possible outcome classes. It evaluates evaluating trade-off between, it is evaluating trade-off between TPR and FPR. Okay. For plotting ROC, it is advisable to assume P is greater than 0.5. Since we are more concerned about the success rate, ROC summarizes the predictive power of all possible values where P is greater than 0.5. Okay. It summarizes the predictive power of all the possible values where P is greater than 0.5. That is why it is a true positive rate, right? The area under the curve refers to an index of accuracy or concordance index. It is also called concordance index. Is a perfect uh, performance metric for ROC. Higher the area under the curve, better the prediction power of the model. I have already explained this. ROC of a perfect predictive model has TP equal 1 and FP equal to 0. I started with this only. The curve which touched the top left corner of the graph. I showed it to you, right? This one. It's talking about this one. Okay, now what I want you to do is quickly create ROC curve. For creating ROC curve, I'm going to create two variables, prediction and performance. Prediction, I name it as ROC pred. Use the command prediction on RES4, and the variable is test.diab $type1. So quickly create this ROC using plot, wherein I mention the data ROC press colorize equal to true means I want to color it. Print cutoffs at sequence 1 by point 1 means every point 1 in your cutoff rate or the threshold, the color will change. Okay, every point 1 in the change in threshold, the color is changing. Quickly do it till 236, and you will be able to, you'll see a ROC curve. You have created a ROC curve. Now once you do this, we will take a break, and we can take a break for 20 minutes today, and we will I'm putting up a timer. Please quickly do it till 236. Couple of more confirmations, or let me share this with you if you are. Two 36 done. Couple of more confirmations on 236. Couple of more. Okay, so I'm assuming that 236 others are able to do 236. Okay, thanks for the response. So what I'm doing is I'm opening the poll. Please do participate in the poll. Let us know how did you do in terms of pace and delivery. And as always, please do come back on time. And the poll is open now. Once you participate in the poll, you may go for a break, and then we will come back in 20 minutes exactly. Okay, I'm putting a timer for 20 minutes, and when all of you come back, we will start with our next algorithm. Okay, hello everyone. Welcome back, and thank you so much for participating in the poll. Please give me confirmation if I'm audible. Am I audible? Okay, so let's start. So we have seen ROCR, I mean ROC and AUC, right? Now this is just the same thing that I've discussed. All the four ratios. Sensitivity ratio, true positive rate. It is also called recall ratio, and specificity ratio is true negative ratio. Okay. And one last thing, how this ROC curve is plotted. I mean, just this is just an additional thing. It will give you an idea how this ROC curve is plotted. Uh, let's assume that uh, we have a model that predicts whether the students will pass or fail, right? So this red one are the actual students who failed. The the distribution of the students who failed, this red one, and the distribution of students who passed is a green one. Okay. So the model predicts probabilities for each student using these probabilities. So this is the distribution, probability distribution. That is what I said, right? Using these probabilities, we plot the distribution as shown. Red distribution represents students who failed, and green represents the students who passed. Okay. Notice on extremes you have, I mean, on both the sides it's kind of a bell shape because on both the sides you have extremes, right? And in the middle you have the maximum weightage or maximum probability. Now we have to pick a threshold value which will predict everyone as positive passed, and below which it will predict as negative. So we pick a threshold. This is our prediction, right? Now this, using this threshold, we are going to predict. If the threshold is zero point 0.5, let's assume that it is 0.5. So below uh, probability below 0.5, which is on the left side of this threshold, right? So all the probabilities on this side, I predict as, what will I predict? All these as failures, isn't it? Yes, I will predict all these as failures, but actually notice these people passed, right? So what are these? These are my false negatives because I am wrongly predicting them as failures, but actually they passed. Is that clear? Is this clear? Yes? And what are these? An easy question. What are these? True negatives. Very good. Right? Very good. Then this on the green side, this one, true positives. And this one, the one in blue, false positives. Right? So this is just an example, and using these four, then we build a ROC curve. Okay. Okay, fine. So you got the concept of how do we uh, decide the classifier, or how do we predict the accuracy of the, how do we get to the accuracy of the classifiers, right? So now what we'll do is we'll move on to the next classifier model and couple of simple ones now. Logistic was a long one, right? It took a lot of time. Couple of simple classifiers we are going to do, and we'll start with SVM. SVM is also called support vector machine. Okay, so we'll do SVM. Okay, so this is SVM. Now, what is SVM? Machine learning algorithm. Support vector machines or SVMs are classification algorithms used to assign data to various classes, right? With this classification algorithms, we are able to assign the data to the respective classes, right? It involves detecting hyperplanes, decision boundaries, which segregate data into classes. Got it? So what does it do? It assigns the data. Let's say this is one class and this is another class, right? Now I need a decision boundary in between classify that will classify these two, right? And then once I finalize the boundary, whenever a new uh, data point comes in, I will use that boundary to classify these. Classify the data point as plus or minus. Okay. Now the hyperplane or this decision boundary chosen should be such that all the points in the data set are far away from it. Means, what does it say? It helps in performing the classification easily. Means we should draw a hyperplane or decision boundary which is as far as possible from the nearest points, right? So if I draw this as a hyperplane, notice that this line is far away from red, but it is very closer to blue, right? On the other side, if I draw this as decision boundary, it is far away from blue, but closer, very closer to red. Are you getting it? So ideal boundary should be something like this one, which is max, I mean, as far as possible from blue and red both. Is that clear? Making sense? Right? Okay. Now, for example, in the given graph, it is easy to classify point A and B as they are reasonably far away from hyperplane, right? If a point A comes, if a new point comes in, right, new data point, and it is somewhere here, right? Somewhere, let's say it is A, right? So it is very easy to classify it because it is far away from the boundary. On the other hand, if the point comes out to be, let's say B is here, let's say D, B is also towards, let's say D, right? Even this is easier to classify, but when a data point C comes in, right, it is not easy to classify, right? And here the maximum errors that are made in terms of accuracy are here only, right? So, but one cannot classify C confidently as the point is very closer to the hyperplane. Okay. Now, this I have already explained. Once ideal hyperplane are discovered, new data points can be easily classified. The objective of optimization is to maximize the distance between data points called the support vectors. Now, the nearest data points to this decision boundaries These three, can you see? Nearest data points. They are called support vectors. Hence the name support vector machine, right? Okay. Support vectors and the hyperplane. This distance is called the margin. The distance between them and the hyperplane is called the margin. You can see, right? Is this okay? So this is just a derivation which is not required. So we just ignore this, right? Calculation and all, right? So all this, in terms of concept, all you need to know is what we discussed. Okay. So now I want all of you to quickly open R, and we are going to run support vector machine on iris data only. So no external data set required. Uh, Activate this package, install and activate E1071. Then view this data and plot iris data. See, plotting iris data looks something like this. Run it and let me know. Once you're done till plot, just type 11 in the chat window. Okay. So if I blow it up, you can see it shows the relationship between, this is the relationship between sepal length and sepal width, right? This is the relationship between sepal length and petal length, right? And so on, right? Okay. Now we want to predict the species, so we will use other parameters. Means I'm going to drop the species because I want to predict species, right? Species is the fifth variable, right? So I'm going to drop the species, right? And what I'll do is I'm going to just plot sepal length and sepal width. Let's plot sepal length and sepal width and see how the plot is created. See, this is sepal length and sepal width for three species, right? This is a sepal length and sepal width. So if you will see, there's a lot of overlap here, right? Lot of crisscross overlapping, isn't it? Yes, in terms of species, there's a lot of overlapping, right? Are you with me? Okay, if you're doing it, fine. But right, there's a lot of overlapping happening here, right? Let's plot petal length and petal width. Look at the data now. So anything striking? There is very less overlapping or very less, yeah, right? The data is very easily, I mean, you can easily see, you can pass a hyperplane, right? And so using petal length and petal width, I can easily pass a line from here and maybe another from here with minimum error, right? Or minimum, I mean, when even when a new data point comes in, it it will be somewhere here. If it is somewhere here, very clearly it's correctly plotted, right? Only the chances of error will be around this line, and that too very less, because you can see very less overlap is there, right? So something like this, we are expecting the SVM lines to plot the hyperplanes, right? Okay, so analyzing the two scatters, sepal length and sepal width has a lot of overlap and not easily distinguishable. However, petal length and petal width can better classify the model. So we plan to use, so we'll use petal length and petal width. Okay. Now set seed, and this time I'm going to use another way of cross validation, and that is using sample command. Sample, once you've done, this line number 31 says create a sample of 100 from 150. So if you run this, notice it has created a sample of random 100 numbers from 150. That is what it is doing. Creating a random sample of 100 from 1 to 150. Okay. Is this clear? What is this doing? Okay. Now I put this in S. I put this in S, and then what I do? I create a variable call which has petal length, petal width, and petal length, petal width, and the last one, species, right? I save this to call. Only the names are there, right? Okay. Now, once I've created a sample and put it in S, now I'm using 100, this out of 150, 100 random samples were picked up. So I'm using them with iris data to create a trained data set. Once you're done till line number 42, let me know. Or 45 rather. In line number 45, I am simply using the remaining 50 observations to create a test data. This is another way of doing cross validation, that is splitting it into train and test, splitting the data set into train and test. So do till line number 45. Okay, we'll wait for others to confirm. Line number 45. Okay, great. Thanks for confirmation. Okay, so once you have created this train data and test data also, iris.test, this is our train data. I am ready to create a model, SVM. And if you want to know more about SVM, it is from the package E1071, which we initially installed, right? So SVM, using the command SVM on species, and then on the left side I put all the remaining variables. So I'm using dot. Then I mentioned data is the training coming from training data, and kernel equal to linear. Now what is this kernel? Kernel is kind of a function that we want the line to be a linear function, right? So kernel means the function, right? So SVM algorithms uses a set of mathematical functions that are defined as kernels. The function of kernel is to take data as input and transform it into the required form. So we are directing the algorithm to come up with only linear lines, okay, or linear models only. So difference between SVM algorithms, different SVM algorithm uses different types of kernel functions. These functions can be of different types. For example, linear, nonlinear, polynomial, uh, radius base, and sigmoid. So we are going to use only linear. So kernel equal to linear, cost and scale. Scale means you are saying, you are asking that if while creating the model rescale the data, right? Do the normalize the data. Okay, and cost means the margin. Cost means the margin. You are saying a minimum, I am expecting a minimum margin of this many units. So once you do till line number 53, line number 53, when you're done, let me know. 53 done. Okay, some of you are still doing. Line number 53. Okay, so line number 53 is done. Now after 53, print SVM model. Print, if I print this model, it will have the details of the model, in terms of equation, and it is saying it has built it on linear kernel with the cost of this. That's it. And number of support vectors 71. Remember support vectors? So there will be 71. There are 71 support vectors that it has identified. Now plot. So when I run this plot, so when I do a plot and zoom it, you can see it has created a you can say linear hyperplanes, very clearly dividing between. Did you get this after running it? Okay. Okay. From this graph, you can see data support vector represented by cross signs. So if you see all these cross signs, right, they are the support vectors. And decision boundaries belonging to three types of species. White color means the lightest color, then second species, and then you have the third species. Okay. Now tune. What does tune do? Tune helps you in analyzing the cost of different margins, right? So what I do in tune is I want to further fine tune this, further fine tune the boundaries. So that can be done using tune, wherein I mention the data set, species, and then I mention the model. Then I say data, give the data. Sorry, first I mention the machine learning algorithm. Then I mention the equation. Then I mention the data, kernel equal to linear, and lastly I mention the range of the list of different types of cost. Okay. So once you try these different types of cost and save it, save this to tuned, and if I take the summary of tuned, So you can see that now which once you are trying different types of cost, right? I want to see which is the cost that optimizes the uh, division between three flowers. Okay, and you can find that by looking at this summary, right? Looking at the summary, you'll see uh, dispersion. Can you see dispersion? Dispersion keeps on decreasing right from the start. Dispersion, and this is the cost and error, right? Now dispersion initially comes to be 0.16 with an error of 0.72, right? Then as I add more, mm, is this? Yeah. So as I add more variables one by one, right, my error is reducing, right? See, error is further reducing. It's further reducing. Okay, and uh, wherever you see it stabilizes, error stabilizes, error is 0.72, then wait, uh, best performance is at 0.02. Wait, how did it arrive at 0.02? Okay, best performance is at 0.05. Okay, 0.05. This is first, second, third, fourth, fifth. Dispersion is reduced. Yeah. So this is right, correct. Can you see? So dispersion gets reduced and it is reduced here lowest, or rather 0.02. It has reduced here the minimum, right? So this is my first, second and third. Third is the minimum. Okay. So wherever this dispersion is the least, that is the cost you will pick. Okay. So from this, when you tune it, you get the cost that is to be picked, and then you can use this 0.05 in the main model. Is that clear? Why do we use tune? Is it clear? To select from different types of costs. Once you run this tune, you get this summary of tune, and from here you can pick the cost. Is this clear? Is this clear? How do you pick the cost? Yes? Okay. Okay. So once you pick the cost, I'll fix it up here, and it's the third. Best performance is at 0.2. Yeah. So here I'm going to pick the third one, 0.05. So on that 0.05, I will again rerun the model, right? Which comes out to be 0.05, yeah, SVM model. And lastly, I use this SVM model to predict and check the accuracy. So use SVM model to predict on the test data iris.test and class type is equal to class, means it's a classification model. And when I run this predict, you can see how it has predicted. And lastly, I create a confusion matrix for this test data and this predicted P is the predicted one, right? So I create a so if I run this, I only get two wrongs, two misclassifications. Okay, so if I see only 0.04 or 4% of misclassification happened. Is this clear? Okay. Those who are doing it, please do it. And based on accuracy, you can always take a decision. So let me know your accuracy rate should come out to be more or less same. Once you're done, let me know your accuracy rate also. My accuracy rate has come out to be 86%. Sorry, 96%. 98, type 98 once you're done till 98, line number 98. Okay, great. So that is support vector. Now let's move to next algorithm, and probably the last for the day is naive Bayes. Okay, can we start naive Bayes? Okay, naive Bayes. It's a classification algorithm based on probabilities of occurrence, right? Probability of occurrence of an event. Okay, so what is a first naive Bayes classifier? What is a classifier? I think all of you would know by now. Any machine learning algorithm that classifies or that categorizes the dependent variable, right? That is a classifier, right? Okay, then why this name base has been given, right? What is name base and why this name base has been given? A name based classifier is a probabilistic machine learning model that is used for classification tasks. This classifier is based on Bayes theorem. How many of you know Bayes theorem? Anyone who knows Bayes theorem or heard of at least? I'm sure because we don't use it often or it is not used, then you may slip. But if you know it, you've heard of? No one. Okay. Bayes theorem you've not heard of. Fine. Conditional probability. Have you heard of conditional probability? Yeah, that's okay if you have not. I'm not asking about. I'm not saying that you should remember. I'm saying if you have heard of, so that at least I have an idea that how many of some prior. Maybe once we do it, you'll get an idea, right? But at least some prior information about it, right? Yeah, probability of an event occurring based on a previous one. Yes. Heard in school. Yes, of course, this was done in school or maybe your college days, right? Okay, so what is the Bayes theorem? It is a conditional probability theorem, right? And we'll see this, right? Hence, because this is based on conditional probability, it is called naive Bayes. Okay, the classifier is based on Bayes theorem, hence the name. The Bayes theorem is used to calculate the conditional probability, which is nothing but the probability of an event occurring based on the information based on the information about the events in the past. Okay, so it makes a strong assumption. Now, why this word naive has come? Right, Bayes was okay. Okay, it has borrowed the name from Bayes theorem, but why this naive Bayes is there? It is there. Naive is added to this Bayes theorem because it makes a strong assumption that predictors or features are independent. Now, this is the assumption that all the independent variables, predictor variables, they are independent. They do not have any, you can say, multicollinearity, right? Or they are not related among themselves. They are independent. Hence, this, and which is actually in real life, it usually does not happen, right? That is why the name is given as naive. Is this okay? This is that is the presence of one particular feature does not affect the others, hence the name naive. Is it clear? Now this is just the concept part. Now let's understand Bayes theorem, right? A little bit about Bayes theorem, so you get an idea about uh, what is how this conditional probability works, right? So from Bayes theorem, right? P A pipe B, it means probability of A knowing B has occurred. Is that clear? Probability of A knowing B has already occurred. PAB, PA pipe B is equal to PB pipe A, and then you multiply this by probability of A and divide by probability of B. Is this clear? Right, this is a formula which you do not have to remember. I just wanted to show you so that this is how probabilities are calculated, right? Now let's take a look. This is a very easy to understand example, right? Which will give you a good idea about conditional probabilities. Okay. Now, based on the training data set below, we need to classify if the players will play based on the weather condition, right? So, look at this data closely for a minute. This one, weather and play. Just okay. Have you gone through? Now, based on this data, what we do is we create a frequency table. So, what have we done? The first step is to create a frequency table of weather and the play, right? So on the vertical axis you can see weather is there, and otherwise on the horizontal side you see yes and no to play, right? And we create a frequency, and very interestingly notice that when it was overcast, play did not happen, right? Now once you have plotted the frequency, you create a likelihood table, means the probability table of each, you can say each cell or each data point in the frequency table. So now once we create a likelihood, or the, notice this how it is calculated. Overcast, let's see overcast. It says when it was overcast, all the 4 days play happened, right? And no play did not, play did not happen. In fact, I would say all the overcast days play happened only, right? There was no case where the play did not happen. Okay, so now what is the probability of overcast? Yes, what is the probability of overcast? It's simply 4 divided by total, which is 14, right? So 14, 4 upon 14. Similarly, for a rainy day, what is the probability that of probability of rainy day, right? So probability of rainy day will be 5 upon 14, and sunny day will also be 5 upon 14. Okay, that's how you can create a likelihood table. Now once this likelihood table is created, then it is pretty easy, right? Uh, and you can create conditional probabilities from here, like this one. This is our likelihood table. Based on the training data set below, we need to classify if the players will play based on weather condition, right? So now we'll see some conditional probabilities. right? P yes, P yes, pipe sunny. It means what is the probability that play will happen had it been a sunny day? Okay, what is the probability that play will happen knowing it is a sunny day? Now, what does this mean? It means I have to just look at this. I'm going to just rule out. So, look at this. Only the red part. I am saying it is a sunny day already given. Now, what is the probability that play will happen? Tell me. Let's see who can tell me this. Anyone? Knowing it is a sunny day, what is the probability that play will happen? Are you getting the question, everyone? I am giving you a condition. Knowing it is a sunny day, what is the probability play will happen? Isn't it 3 upon 5? Isn't it 3 upon 5? Knowing it is a sunny day. I already know it's a sunny day. So I will rule out all other conditions. Right? Y point to 1. Knowing it is a sunny day. So what is the historical probability of all sunny days that play is happening? It's 3 upon 5. Did you get it? Did you get this? Now give me, I'll ask you one more question. Knowing it is a overcast day, what is the probability that play will happen? 100%, right? Knowing it is a rainy day, what is the probability play will not happen? No, play will not happen. Pongodi, 3 upon 5, right? Okay, another one. The play happened. What is the probability that it was a sunny day? The play happened. What is the probability it was a sunny day? Notice I have reversed it. No. 3 upon 9. See, the play happened. So I am only concerned about yes part. The play happened. Got it? Right? What is the probability it will be a sunny day or it was a sunny day? 3 upon 9. Clear? Right? That's how conditional probability works and that's how naive Bayes also works at the back end. Okay? And based on these, it creates the probabilities. Okay? Can we now go to R? And I want you to quickly, okay, install these packages. I think all of you would have already installed all the others. Just install naive Bayes. I'm sharing this naive Bayes and then activate these 4 packages. So once you're done installing, I'm going to pick this file. Oh, I think I did not share the file. Wait. I'll have to share this file with all of you. Naybase files. Please, I've already shared that advanced that. Reading from external sources, see. See, it's there. Descriptive statistics. Okay, fine. Quickly read.csv and pick up the file naybase. Structure of this. Once you have put the file, let me know the structure of this file. Structure. Run structure till 17. Once you're done, let me know. I'll explain what exactly is this data about. Once you're done till 17. Once you're done till 17, let me know. Once you're done till 17, please let me know so that we can quickly proceed and complete this. Okay, 17. Pungodi is done. Very good. Others? Now this is a data set from the bank. Okay, where you can see there is a variable called default. Okay, default is our dependent variable and output is either 1. 1 means the person has defaulted the credit card and 0 means he has not defaulted. Okay. Then you have this checking status. There are some status reminders whether the reminder was given to the customer or not. Okay. Then duration, time the credit card bill has been generated. So it is time. History of the customer is available. Purpose of taking the credit card. And notice all these history, purpose, they are all in codes. Can you see? Some codes are there. History also, some codes are there which we don't know the value. I don't know the value of those codes. Even then, we can apply this machine learning algorithm. Okay, amount due. Amount means amount due on the credit card. Savings, saving category, then employment type, installment, then residence type. Okay, apart from that, couple of more, um, residence type, age, other plans if he is holding some other plans with the bank, and how many cards he has, and lastly whether telephone number was available or not. So these are some of the variables, right? Using them we will uh, create this model, right, on naive base. Okay, so now you'll see clearly that default has to be a factor type. Apart from default, installment and duration. Okay, so I am converting all the three into factor type: installment, duration, and default. Convert them into factor, and when I do this, if I again check the structure, I'll see default as factor, installment as factor. Yeah. So duration. Why is duration? Okay, maybe I did not pass the command. Installment is there now. So these three. Then let me check. I've already checked. Now I have factor, and uh, installment and duration. Duration is not converted now. Duration is okay. I'm converting into numeric. Fine. Next, once you do this, I'm creating a cross tab just to get a better idea of this installment spread. I'm creating a cross tab to get an idea about the how the data is distributed among the with different installments, right? Once you have done with installments, we'll start. Once you have analyzed the spread of installments, let's create split the data. 1000 observations are there, so I'm splitting the data using sample command. And sample command, another way, right? I think we have not done sample till now, right? To split the data. Sample, within sample, I mention two. How many samples I have to create? Two. Then n row b nb. Nb is my naive base, right? Data. So you can see n rows is total number of rows. 1000 rows are there. Replacement equal to true, and probability of um, train and test, right, is 0.8 to zero point 0.2. So when you run this along with set seed 1, 2, 3, 4, once you have assigned it to IND, I'm using IND. Test train. Quickly do test train, and then you can check the structure for test and train, and you'll see that in test data you have 792, and in train you have 208, so that the total is 100. Now, just I'm just observing the behavior of customers here using dplyr package, and if you'll see, I'll share this with you. Run this and you will see the mean and standard duration of people who defaulted. Notice that the mean and the standard deviation of the duration is comparatively more, right? It means it will ring a bell if you are analyzing, it will ring a bell that yes, something is wrong with this particular group, right? The mean is also high, as well as standard deviation is also more, right? So this will give you a hint that where there is an issue, right? Do it till 83. Once you're done, let me know if you're done till 83. After you're done with 83, activate this library, naive base, activate the library, and then naive underscore base is the command for creating the model of naive base. Once you are in the naive Bayes model, first I mentioned the equation, I mean default, the model equation, default is equal to installment plus duration. So we are just creating a naive Bayes model based on installment and duration only, right? Data I'm mentioning as strain data, and use kernel I will always mention as true. And when you run this and you come up with output, Laplace, you can see Laplace equal to 0. It's a smoothing technique, whether it is being used or not. All you have to, I mean, if you want to know more, you can read it through web, but it's a smoothing technique. Rest, you can see the how many samples were there, classes, two classes were there, right? The naive Bayes classified into two classes, 792 train data, right? Then you have conditional distributions, categorical and prior probabilities of 0 and 1. So this is how the summary looks like. Once you plot this, it will plot density versus on duration for 0 and 1. So I mean this is not required for taking decision, but yes, you can plot this. Once you have plotted, we will uh, predict the accuracy of the model. Sorry, first we'll make prediction using the model, and I am assigning the prediction to P. Predict is the command, then you mention the model, and then you say the new data is equal to test. Means new data is a term, right? It's a command. New data, put it and mention the test file. So new data equal to test and type is equal to probability. And this is how the new data has come up. After you have got the new data, after you've got the prediction values, I'm combining it with prediction with test. So you can see prediction with the default earlier value. And this is the predicted values, right? And lastly, I'm just predicting on test data. To test the accuracy, I'm predicting it on using this NV model on test data. And once you use this model on test data, after that you create a classification, oh sorry, confusion matrix. You create a confusion matrix using the command, using table command, and then last in line number 127, you calculate the accuracy of the model, which comes out to be 67%. Once you're done till 127, let me know. So that is it for today. We have done 3 models. Yeah, almost 3. 127, once you're done, let me know. Okay, so tomorrow we are going to start with KNN, and we will do 2 very important models, uh, decision tree and random forest, right? And then day after tomorrow we'll do clustering, and I think we should be able to manage Lubridate package as well, right? The way we are going, good. I think we are on track, and we should be able to manage, or that advanced statistic, we can do that as well, right? So 2 more days, and we have around 3 or 5 models to go. Okay, then. Okay then, right? Thank you so much, everyone. Take care, and we will continue our journey tomorrow and day after. Okay, take care. Bye. Good night.